Okay, so let me start by revising what we learned last time, maybe in a little bit different notations. So basically, what we learned last time is that if my the time dependent Hamiltonian that I take, usually in scattering computations, what we do is we consider this to be of a kind of adiabatic approximation. So it starts out from 0 at some point, starts out at 0 at minus infinity, t equals 12, plus t equals to plus infinity, it again goes back to 0. So in the middle, it is a slow function of time which at some point rises and again decays and goes to 0 at t going to infinity. So in that case, what happens is that u plus infinity minus infinity acting on the free theory vacuum, which is also the case at time t going to minus infinity, is basically just a phase multiplied by this. So, in a general setup where, let's say, the vacuum of the interacting theory is omega, then this can be written as this. And what we essentially do is we multiply the phase here, take this to the power I here, which in fact, so this thing I can treat as this. This part goes here in the denominator, which is just and this, the 2 of this will ultimately result in plus infinity to t. So the full evolution in the numerator is minus infinity to t, operator insertion, and then t to plus infinity. But this is again valid for this adiabatic approximation case. If I have a more general time dependent Hamiltonian, in which case this does not hold, so what happens is that it more general HT, which is basically not adiabatic approximation. Adiabatic approximation doesn't hold. So this expression will just, you have to somehow write this. Where, so this expression looks like I'm starting from minus infinity going to t, operator inserted, and again going back to minus infinity. So if I want to compute something from this kind of expression, I want to be able to avoid the discussion of or the reference of the state at plus infinity, which Finger Kelly's restriction enables me. And so let me basically, as there was few confusions last week, we clarify a few things in different notation. So let's say I write my density matrix. So I will always need doubling of fields when I talk about density matrix, because this is the operator in the Hilbert space, or this belongs to the operator in Hilbert space. And we previously discussed that if state space is d-dimensional, operator space is d-square dimensional. In other words, for writing rho, I need basically this kind of thing. So one thing from the gate space and one thing from the dual or conjugate vector space process. So we write this in this way. In terms of the fields, wave functions. By phi prime, I am just saying it's a dummy index switch. And in the path integral notation, psi k and phi 2. Let's say phi 2 is defined at time t2. This is the evolved field. Start from psi k phi 1 defined at 1 to something like x bar t1, which I was in the previous day I was writing in terms of everything like wave function in the position space and so on, but now let's write down in this notation. If we follow this, then if we go to a density matrix, I need phi 1, phi 1 prime, I need this phi prime, so e to the power I is of phi minus is of phi prime, and psi k phi 1, psi k star phi 1 prime, along with, let's say, this lambda piece, and this is my rho at phi 1 prime, and this I am evolving this way, then what I get is rho phi 2 prime. So if I now take the trace of this density matrix, and basically which will be unity. Phi 2 over this field. In case I have to identify phi 2 prime, like if I had a density matrix of this kind, by taking place only this kind of states will be there. So this is the function here. Now I will just use this expression over here. Then what it becomes is 2 phi 2 prime. Now what we'll do, if you remember from the discussion the last program, we also have a phi 1. So if I what we do is that while performing this integration, after taking into consideration this delta function, so this d phi 2 and d phi 1 then defines for me that I'm starting from my starting phi path in the path integration. It starts from, let's say, phi 1 goes to phi 2. The phi 1 is defined at the first state that I defined here. So these integrations are needed for the boundary conditions. This will in fact be treated as a boundary condition. So basically what I will write down is this part now, the path integral notation. just treat these two as the corresponding boundary conditions. So over here I will write rho I, which will be like rho phi 1 phi 1 and over here I identify phi 2 as 2 phi 2 phi 2. So this is my what is called the Schindler-Keldy's generating function. But this is again in absence of forces. I haven't taken the action itself. I haven't taken any further forces. And this is just unity from this, in absence of sources, this is unity from this trace factor that from where we derive this. And the action, basically what I, after I put these boundary conditions, I just want to consider one contour which will not be time ordered, but this is a, like, you can think of this as a path ordered contour, where the path is this closed contour that I have, which is typically called contour ordered as well. So I start from some minus infinity, I evolve, and basically I was identifying the phi 2 with the phi 2 here at time t, and then I backward evolve and so on. So this phi 2 or phi 1 was here, phi 1 was here, and here the things are also, this is a closed contour because over here also we, if we close this contour, we get this density matrix rho phi 1 plan. And so now we can, if we just write this as a single contour, you don't have to deal with all the different kinds of fields. So, okay, we can, but a more simplified version can be possible. So from now on, what I will do is this d phi part is the above part where it is forward evolving, and here it is backward evolving. So here I can see my contour is going left and here it is going right. So all of the field integrations that I will perform here I will call them phi r, and the operators I denote by OR. Here denote by phi l. So this is actually, here we discussed that the Schindler-Keldy's action defined in terms of the phi r and phi l will just be, so phi r, this kind of expression. Here we see that this S phi r and S phi n, they do not have any mixed terms. So this is basically this breaking of non-validation of Sandaric approximation can also be true for a unitary QFT as well as for a non-unitary QFT. So for a unitary QFT, this will be true. I'll just be able to do this. Basically, if I, let's say I have a density matrix at rho 0, but this density matrix is defined on a unitary system, so it is still evolving unitarily. So that evolution, we all know that this is just u rho 0 u dagger. Where this u is, so rho t will be this. Basically most generically secondary terms. So this will be the row. So this U is still evolving unitarily. So say a mixed state evolution. It is valid for pure state density matrix as well as general mixed state density matrix. Evolving unitarily. So this process does not introduce any entanglement along the evolution. In other way, you can write as T, which will be minus phase. This is the entanglement entropy at time T for this kind of unitary evolution of a density matrix. This one can show to be equal to case of rho 0, just you have to just use this thing. The entanglement entropy does not really change, which means that it does not introduce any further entanglement. It could be that the rho 0 that you started from could have a could be a mixed density matrix, in which case the starting entanglement entropy will not be 0, but over the evolution the entanglement entropy will not change. So it is like evolving under a Hermitian Hamiltonian, full system evolving under a Hermitian evolution, Hermitian Hamiltonian, and this evolution will be a just unitary evolution of full quantum state. We are just writing in terms of the density matrix, for which is a more general extension. Yeah.
In that, you are integrating with the d phi 1 and d phi 1, or taking the trace.
Yeah, I am actually using this part to make this identification, this part to write the state at the initial state.
And that integral is 1.
The total integration is 1 after performing this part. Yeah, if you put this as boundary conditions, that will also. So this is basically equal to what I started with. This will be 1 for, yeah, at least for sourceless case. So in unitary QFT, SSK does not have RL mixing terms. But we will see that in non-unitary case, does have RL symptoms. What happens is that, okay, so firstly, another thing is, so if I draw this full contour, this is my initial, and here I identify these two parts, and R phi A at different times. So, this is my imaginary time. This is my so I already mentioned in the last day, but let me mention again. So there could be if I am, let's say, computing a 2-point correlation function, then it could be of 4 different kinds. I could have operators instructions here and here. If that is the case, then this will be time ordered because I am evolving like a forward time evolution, usual forward time evolution. So this will be the case where I have time ordering. If my operators are here, this is backward evolving. So for this kind of operators, it will be anti-time order. So which I am denoting by this T3 and there will be two kind of terms which will be not time ordered, no time ordering at all, which will be just this kind of diagrams. If I have an operator here and here, or if I have an operator here and here. So in these terms, I just have, for example, this will be something like T of T2 T1. Basically, if I have OR T2 or T1, that will be time ordered. Get rid of this because in the whole compute, I will not treat any operator in different parts of it. I can in the previous notation I wrote in terms of phi A or phi A, but in terms of when we think of general operators, we just need where the operator is inserted. If it is inserted in the upper branch, I will associate the R symbol with it. In that case, this will just be time ordered correlation function. If I have ON into T1, this will be time ordered, and this will be anti-time ordered. Each end we will have to consider something like OT1 or OT2. And there will be other terms like LR correlations, which will just be no time order correlations. Also write down a couple of, let's say, so what happens is I have a couple of points that we wrote down here. One is that the state propagators. So whenever I in the upper branch, I will name them as state propagators. For example, this kind of case. These are time ordered. And graph propagators are anti-time ordered. And in that can be boundary condition at final time T, which was like phi 2r is equal to phi 2a. Here my field is phi 2r and phi 2a. This indicates a bracket propagator of this type. And these propagators are in fact computed on shape, which is obtained basically basically by putting the exchange particle function. And these are basically named as these propagators. Are called cut propagators. For example, if I had phi r in both sides, I'm trying to compute the two quantities function, and this kind of case I'll write down this way. If I have phi l in both sides, I'll say write it in terms of dotted lines, which is this case. And these two cases I'll write down either half of the line will be dotted, half of the line will be solid. These things are called cut propagators because in the middle somewhere I'm representing the propagator as a pattern. This kind of propagators. There is no time on it. The representation of those things are of this kind in a diagrammatic way. Because I want to, in the propagator, I have my phi r and phi n fields, which I have to differentiate. Yeah. If the operators are inserted in the opposite branches. But for a unitary QFT, this will be the case. For a non-unitary QFT, for example, here we are still treating with a thing which is evolving under a Hermitian Hamiltonian, and let's say it is a mixed density matrix, but in a evolving unitary. In a non-unitary case, I will have something else which will be like there will be a cut vertex as well over here in the point where you introduce these things, change from solid to dotted line. So this is for non-unitary cut operators, cut operators. These were for unitary. And this cut operator will essentially mean we have some effect of environment as well in this cut vertices, and this effect of environment will be basically written in terms of what I call that RL mixing terms. That I will write down how it comes, I will discuss now. So these are called basically Wakeman rules of unitarity, which we will discuss in the next lecture. In the non-unitary case, I am going to, it is not going to be unitary, so there will be some effect of getting rid of an environment, integrating out an environment. So let's say, yeah, I'll have a q degree of freedom, I'll have an x degree of freedom, I'll have d phi and dx both. Then I will have to introduce dq prime and dx prime. Then I integrate this dx prime as my environment now. Integrate out this part. And this integration will give rise to a term in the Schwinger-Keldysh action, which will be RL mixed term. R and A. Phi R and phi L mixed terms. Sorry? Yeah. The cut propagator is of this kind usually in unitary case. There will be nothing, no cut vertex here, but the cut vertex is again a diagrammatic way to represent that it is non-unitary. In non-unitary case, I have to introduce a cut vertex, which will, if you look at this part, this side is dotted, this side is solid. In the middle, I will have some environmental effects, which will be the effects of this phi r, phi n kind of mixed terms. in the Schwinger-Keldysh action. These are called Weltman rules, which we will discuss the next day. But let us now discuss how this mixed terms appear and how we can motivate them from, let's say, something like an Lindblad equation. So these mixed terms are written in terms of something. This were described first by Feynman and Werner. Influence functions. The main point is that the statement of this is that the process of passing from microscopic, the microscopic thing you can think of as the unit QFT that you are dealing with, microscopic variables to macroscopic ones. When I say macroscopic, I basically mean I have integrated out a part of it. So the integrating out is basically means post-graining kind of thing that I am doing. In that sense, I am saying to be macroscopic induces some interaction between the two Schwinger-Keldysh copies, phi r, phi a. And the generating function of, let's say, the system part of this form. This will be what we are going to call Feynman-Werner explain functions. These are a couple of points which I don't have any further comments to make. These are typically sent in UV and only arise in IR after the irrelevant modes or the environmental modes are integrated out, and this is related to various various IR phenomena. Entropy, dissipation, decoherence. In the previous case that we dealt with, where this was not there, we already saw that entropy did not change at all, the entanglement. So that was not giving us any further or interesting physics after evolving this in this way. But in this case, these things are not trivial. For example, this will give rise to entanglement in the density matrix.
So we don't have this interaction between fire and fire.
Yeah.
So going to theory is still equality there.
So
Theory is still not in there.
I'm not saying that. I think what I don't understand this statement completely, but what I think what they are trying to say is not about that this term will not be there. We will not be able to completely define a consistent theory in the UV using this influence functions. In the IR, you can define these things most systematically. So the IR will be came across this statement. We said they'll have to look a little bit more.
So it is not like that you start on a theory while you don't have this interaction now. But then if you integrate this maybe degrees of freedom, so that's why you are generating this kind of terms, and it is not
one way maybe absent might mean that I have to integrate over a large number of terms in case of IR, in which case it becomes substantially effective. In case of I just only get rid of some few terms, the SIF that I will get, it will not be able to show me substantial non-unitarity. It might be the effect of integrating out will be very small, whereas when I say IR, might be I am integrating out a, let's say, a large bar, due to which this term will be more effective, or it will affect, it will make this term more and more non-unitarity, when it can affect computations of variables and quantities. So another side note is that, let's say if my, so this was for, okay, let me come back to this. Now let us do a simple example where you can see how this influence function comes out. Before going there to more things, so this is just for the non-unitary case, but in the unitary case I can have two further variances which I did not discuss, which is firstly I can have sources which will not be mixed terms of phi or phi l, but I can just write them in the following way. In that case, the still into GR J will be phi r phi l by the previous SSK that I had. Plus dt jr phi r plus j phi. Where jr and j are the sources corresponding to the phi r and phi n branch. And yeah, so this is one case. Another case is if my initial state is thermal. So then basically my rho I that I have will be something like a temperature, inverse temperature at time 0, or the initial time, and my Hamiltonian at time 0. This will be my rho initial, that boundary condition I was putting here. So rho I to phi 2r to phi 2a. We have this. Basically, in the, if you remember in the correlation functions, what we were doing, O1, this was, we are taking basically O1, O2 with contouring, ordering, so 1, 2, along with a rho initial at minus infinity, which one, or at initial time. So this initial time thing, if it is a thermal density matrix, this will also introduce a e to the power minus beta 0 e0 term, which again we know that we can associate this beta 0, write this beta 0 as something like I tau, which is imaginary time. And then what happens is that the contour will look like this. So the usual things that I need to do, let's say I start from t plus I epsilon, or t0 plus I epsilon. This is my real line where it is t0. You can think of this t0 as this kind of infinity. Here it is t minus I epsilon, where I come back at t0. But due to this beta 0 part, I have to perform a further imaginary time contour part. Which will be until this point, and this point is basically t0 minus I epsilon plus beta 0. this part of the imaginary integration one has to do if only the initial state that we start from is the thermal state. But it is still, we are discussing in terms of the unitary safety, so the unitary QFT. So this is the full state. They have not integrated out anything. Now, what we will see is example coming back to the non-unitary situation. The discussion of the finite Warner difference functional. We will see an example of that. Example. So let's say if we consider a linear system with 2 degrees of freedom and the Lagrangian is written this way. Q dot is dq. Usually we are finding Lagrangian plus we have a harmonic oscillator. And I have a qx kind of mixed up. So this is my LR. So just to make sure that I have in the Lagrangian I have a coupling part as well. So in the path integral level, what happens? The finger like this path integral will be something of this kind. Do phi r, do phi a. So dq r, dq a, dx r, dx a plus 1 into the 2 branches. Then I have 3 power and finger range of q r, q a plus I x r, x a plus I S I, this part of the Lagrangian, Q R, X R, Q A, X A. And say my total state of these two systems, initial time was y, and here I have to make identifications of this time. Q R equals to Q A, the final time, and X R So what we will further assume here is that the initial density matrix that I start from, which was also true in case of our previous quantum mechanical open system discussions, that we considered this to be a product density matrix of this kind qi q cross qi x. Then I can divide this integration and write it in this form. Y q bar to the power I from the English of QR QA. But then in the rest of the part, if I treat this QR QL system as my system part where I want to focus, then I will have to do the rest of the integration, dxr, dxl part with all of the things that had dependence over this xr, xl degrees of freedom. So with this I will have a further term which will be the integration over this rho x part, and here so this part is identification of this is left still. Here I will make this identification, I will perform this integration. dxr dxa to the power I plus R inside. remember that this part that I am writing is SK, QR, 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 QL, or XR, XL. These are again just SK of S of XR minus S of XR. This part has this mixed terms. If I perform this whole integration, this will give rise to this part for QR, QL, because I have integrated out this XR, XL parts, everything. So the function of this kind, and which you can also write it as this. After integration, I can write this term as function of this part. This is called the influence function. This phi is called something influence space. So to see more clearly what will happen is if QR, QL, let's say I start from some time tau. This was time tau. And this time t. Then this calculation can be done in terms of which final form that comes out is basically this kind of integration initial time is at tau and spending time is at t. This influence function that comes of this kind. Here you can see you have mixed things of QL and both QL and QR, and this will be, for example, one example of this influence function. And once this influence function is there, this evolution will come out to be non-unitary. In fact, what we discussed earlier when we discussed this GKSL or Wingblad equation, this influence function can be written in a more general form.
Passing from microscopic level.
Yeah.
That derivation of this example. That we are doing
This, if or typical I phi 0 that I wrote, that was done after getting rid of this, after doing this DXR, DXL integration, which were my environmental degrees of freedom, let's say my Q and no. Q is one degree of freedom, X is another degree of freedom. So for Q I had QR and QL, then I double the degrees of freedom for defining density matrix. For X I have XR and XL. I have this kind of integration. I am integrating over these degrees of freedom, so whatever I get dq I in that part I will have this I50 which is a mixing term, which will be a result of this integrating out. So in terms of the general case, this influence function was can be actually written in this way with another formula yeah, so this influence functional actually has mixed terms. All of these terms are basically derived to non-uniform. But apart from these mixed terms, these kind of terms are also there, which are just phi r and just phi a kind of terms. And if you look at this expression carefully, this looks very similar to what we had in the GKS equation, where we had, apart from the Newtonian acting on something, commutated part, we had this kind of a sum. So here also you can take different kind of operators like one can take a sum and produce a gamma. Here also we had this is a P minus alpha. This was my full term here. So this kind of terms as a, because here ultimately it is going to act on something. This is just a generating function. When we try to compute some operators or expectation or correlation functions, we'll use this as this time ordering part, this time contour ordering part, but otherwise we'll also have this O1, O2, initial states, etc. So the whole thing will still act on something. That something is like this. So it is very, what I want to make is this is very similar to GKS. And in fact, we can do an example which I might jump some steps here, but it will be the full derivation will be in my notes. But an example where we can see this explicitly, that if we integrate out certain things, start from this GKS equation, then basically there is a way to write down the path integral version of that GKS equation, which will come out to be exactly like this. So GKS equation like this. matrix, everything is system density matrix. So if we discretize my space to be able to at some point write down this as a path integral notation, we'll have this, for example, this will have indices like rho n, and I'll have position indices as well, position space indices like xn, xn plus 1. So let's say everything I am doing in n plus 1 step, and at different positions. One is, again, you can think of as this, this has two copies, it's n plus 1 and this particular version. Then in the part-derivative sense in which we derive this equation previously, we can write it as 1 plus epsilon into some element into rho of n, which is the density matrix at nth time step. Remember that we derived this density matrix equation in that part-derivative manner only. Then what we can do is go to momentum space. Really not really going to about it. Then what we can do is explain into this and then introduce some more variables, dxn, dxn prime. Then see this term will be there. Then I have a dxn plus then I can basically take this one part separately and epsilon hidden part separately. Where in this equation what I have is the, if you remember, this is the epsilon ordered term because I subtracted the rho, this multiplied by the rho term already. Sorry? This is at, so in your path integration, you divide everything like you have two paths here. You divide it in many steps, right? Which are like you can think of them as time steps or those things. But some nth thing and n plus 1 step, which is what I am looking at. And again, in that sense, I can write the rho n plus 1 in terms of rho n in this way. In this quadratic sense, where this was also the way we also derived this equation quadratically. And then, since it is d rho dt, I will get rid of this part. The rest of the part that I have here, ln, is basically the, I was writing this as L acting on rho. Then that version in its level will be my ln. So this part is what I will be finally able to write here it will come Pn minus IH rho n plus IH. Everything that I am doing here I will just do here in terms of ln. These are early n, remember, and my usual n's are sort of the operators that I had in this equation, which were quadratic versions of the Gauss operators. Somewhere I will have this. Then I can again write everything. Basically, what we have to keep doing, there is nothing very physically insightful going on here, but if we keep doing this and add all terms that I get from here, then we just write down the final expression, what it looks like. But this or IPX kind of terms will come out from this kind of this overlaps. Everything is a function of molecular position. You will have minus prime term. If you look at this, this is already kind of the Singer-Keldy's case of usual fields that we had. So this is for this x, you can think of as phi r that we had previously, and the x prime you can think of them as phi r prime derivatives, phi n.
How do we get this? This factor x prime, dm prime, x prime, and this last factor. Yeah, that one. Yeah, this one.
This one. This one is I started from xn plus 1, this things. Then I firstly inserted one dpn prime integration. This will give rise to xn plus 1 pn integrations. Then I insert another dxn prime. This will insert xn here, again xn here, then xn kind of things here.
So we have pn prime, this pn in the.
Oh, sorry. Okay. This is not pn, this I wanted to write. And first we have a prime over here. Then I have a xn prime. Pn xn. Then I have a rho term which I get rid of. So this term I will not have actually, because when I compare with this expression, I just want to take this part. So in that part also, this xn prime will appear. There will be no term like xn, but this will be xn pn prime, then pn prime, xn plus 1. This is the term. Here you can see this will give rise to a e to the power something like ip n xn prime, or prime xn prime, and this will give rise to e to the power minus ipn prime xn plus 1 prime. So if I combine these two, I get something like e to the power minus ipn xn plus 1 minus xn plus 1 prime minus xn. So epsilon. I actually have epsilon ln into rho. So when I take the plus one part out, and always have this kind of term. Again, if I go to rho n plus 1, and so if I write this as some rho at time, final time, sandwich between this kind of things. dp dx prime x prime into 2 power I plus from the terms, and which will this part will actually x6 dot x prime is dot prime and so on. Further terms that I have further two terms, if you can see this part already. The first term that we have is a mixed term of, let's say this is a phi r, this is phi n. I have a mixed term of ek, and the ek dagger is a function of phi r, phi n. In the second and third term, these are both function of p and xn, p and xn. So these are just phi r terms. And this is again phi n terms. So the influence functional that I wrote earlier, which was basically this if part, apart from these parts, was equivalent of this phi r kind of function, influence function, and we can already get starting from that expression, and if we write up that particulation in this way, the GK equation is defined after this W of degrees of freedom. This kind of functions where there is one mixed term of phi r, phi n, or here p and prime and x and prime, and two other terms which is just either function of phi r or either function of phi n. P and x and p and x and p prime x and prime, p prime x and prime. So this is the relation between the GKS equation and the influence functional. So the influence function, you can, the general version of influence functional that one uses in QFTs as well, nominated QFTs, that has a similar form as the GKS equation, and you can derive it starting from there. This was for a simple, let's say, unnegotiable kind of thing in the position and momentum space, but we can easily translate it to quantum field theory. Okay. So this was what I wanted to discuss today. The next day, what I will do is I'll discuss more about how. Next lecture, we discuss the Feynman diagrammatic rules for this kind of non-unitary QFTs, which are actually called also called Feynman rules of unitarity. which depending on whether your theory is unitary or not, basically which says that this is dagger, this is the scattering operator, it is identity or not, they can write in terms of this 1 minus T and 1 minus T dagger. These are the transition operators. So in terms of this I can have a relation which for a unitary QFT it has to follow. Depending on whether the transition amplitude follows this relation or it does not, I will have certain rules which are called Venn rules, depending on which I will motivate how the diagrams are drawn and how basically the corresponding terms are written. For example, the out of time ordered correlators or the time order and time ordered correlators, everything. And finally, we will discuss one example of open quantum field theory, which is a non-unitary quantum field theory for, let's say, 5 cube plus 5 to the power 4, or let's say one of the 5 to the power 4 kind of interaction terms. For field theory part, I have actually 3 or 4 references. So references are, first is Chandran Jana's PhD thesis. You can find it in Inspire HD. Second is there's a book on non-equilibrium. So as I mentioned that this in vacuum not being equal to out vacuum, the thing that is essential for dealing with Schwinger-Keldysh comes out from the fact that the system goes out of equilibrium. So there is a book on non-equilibrium quantum field theories. There's a book by Alex Kamenev, which is called Field Theory of non-equilibrium systems. Then there is a nice introduction of Schwinger-Keldysh given in a paper by these people. The archive number is this. Here you find in the first few sections there is a very nice introduction, more detailed as well, introduction given about these things, Schwinger-Keldysh and everything, details of Schwinger-Keldysh, and these particular derivations starting from the Lingard equation and coming to this path integral version of this influence functional. This I took from, there are some open QFT lecture notes given by lectures given by Chandan again. Which are given in ST4 2017. The lecture notes are available in, you can go to ST4 2017 website and this lecture notes are available. This derivation is taken from there. These are 4 main references that I am following, and